morning, students. In this presentation I am going to discuss about 5 different and important chemical reactions of hydroxy compounds, alcohols and phenols. First I will discuss about the diazo coupling reaction. This is a very important chemical reaction which we will use in our laboratory class also to confirm the beta-naphthol and primary amine, that is primary aromatic amine aniline. Okay. Let us see what is a diazo coupling reaction. Diazo coupling reaction is basically an electrophilic aromatic substitution reaction. This reaction occurs when arene diazonium ions are reacted with the highly reactive aromatic compounds, that is phenols and tertiary amines. The product obtained is a iso compound containing the N double bond N. The two aromatic systems will be in conjugation through the N double bond N. Therefore, the obtained product will be having a characteristic color. By means of this particular color, we can able to determine the primary aromatic amine and also beta-naphthol. This is the general reaction of the diazo coupling reaction. As shown in the slide, this is the arene diazonium ion which will undergo reaction with the highly reactive aromatic system. Here Q may be a alkoxy group, hydroxy group, or maybe a amino group, and this is the iso compound that will obtain. This is the aromatic system having the conjugated bonds. This is also another aromatic system having the conjugated bonds. These two aromatic systems are linked through this N double bond N. Arene diazonium ions are basically weak electrophiles. Therefore, if they have to undergo the electrophilic aromatic substitution reaction, then we require the aromatic systems which are highly reactive, containing the groups which can pump the electrons into the aromatic system. Let us see the mechanism of this reaction. This is the electrophile, that is arene diazonium ion, and this electrophile will undergo reaction with the aromatic system. Then we will get this particular product, and to retain aromaticity, the H plus will be abstracted by the halide ion. Then we will obtain the final product. That means this is a, we can say, a simple electrophilic aromatic substitution reaction. Let us see different examples of this reaction. When arene diazonium cation undergoes coupling with a phenol, then we will obtain this particular orange solid. This is known as paraphenylisophenol. Let us see other example involving the amine. When arene diazonium ion undergoes the isocoupling reaction with a tertiary aryl amine, then we will obtain this yellow color solid. That means the color of the iso compound will depend on the nature of the aromatic systems that are in the conjugation. As we observed in the previous examples, generally the coupling is taking place at the para position. Whenever the para position is not free, not open, then coupling will occur at the ortho position. As you see in this particular example, the methyl group is ortho to the hydroxy group. Therefore, the para position is not free, not open. Therefore, this diazonium ion will undergo electrophilic addition at the ortho position to the OH. Since this particular para position is not open, it is occupied by methyl group. Let us see the coupling with the phenols. Whenever we carry out a diazo coupling reaction involving the phenols, the reaction has to be carried out in the presence of a slightly alkaline medium. If we carry out the reaction in a slightly alkaline condition at a pH above 10, pH below 10, then the reaction occurs at a rapid rate, because phenol in the presence of a basic medium will be in the form of phenoxide ion, and phenoxide ion is more reactive when compared to the phenol, because phenoxide ion, this O minus then can donate the electrons to a greater extent when compared to the simple hydroxy group. Therefore, because of the strong resonance effect induced by this particular O minus, which is attached to the phenyl ring, this is a highly reactive aromatic system compared to the phenol. Therefore, this will undergo the electrophilic aromatic substitution reaction with the diazonium ion, that is a weak electrophile, more readily when compared to the phenol. Therefore, if the solution is more alkaline, if we take a strong base, then the reaction does not take place, because in the presence of strong base, the diazonium ion will change into diazo hydroxide, and also it can be also changed to diazotate ion. Therefore, because of the conversion of the free arene diazonium ion into these type of these two species, the diazonium ion will not be free. Therefore, it will not undergo any diazo coupling reaction with the phenols. This is the coupling reaction with the beta-naphthol. This reaction we generally carry out in our laboratory. We take the arene diazonium ion and we will react this with the beta-naphthol, and generally the temperature will be in the range of 0 to 5 degrees centigrade. We will carry out this reaction in a weakly basic medium, and since the para positions are occupied, they are not free, they are part of the fused ring, the substitution occurs at the ortho position. Therefore, this particular arene diazonium ion will couple with the aromatic system in the ortho position, and we will obtain a beautiful orange red dye, and the name of this azo compound is phenyl azo beta naphthol. By using this reaction, we can identify the beta naphthol, and also we can use this reaction to identify the primary aromatic amines. From aniline we will obtain this particular diazonium ion. Therefore, aniline also can be determined by using this reaction. Let us see what will happen during the coupling with the amines. In the case of coupling with the amines, we have to maintain slightly acidic conditions. If the acidity is very high, that is the pH of the solution is lower than 5, then automatically what will happen is the amine will undergo a transformation to iminium ion, and these iminium ions are unreactive, because here the nitrogen is having the positive charge. Therefore, and when it is having the positive charge, then this ring will be deactivated by the positive charge of the nitrogen atom. Therefore, positive charge on the nitrogen atom. Therefore, these iminium ions, or rather we can say iminium salts, will not undergo any coupling with the diazonium ions. Already I have explained that the azo compounds are having a characteristic color. This is due to the fact that the two aromatic ring systems are in conjugation through this N double bond N. That means the conjugation is extended beyond this particular system into this system through the N double bond N. Because of this extended conjugation, they will absorb the light in the visible region. Therefore, they will exhibit the characteristic color. Then what is the important application of this diazo coupling reaction? In the diazo coupling reaction, we are obtaining the azo compounds, and azo compounds are having a characteristic color. Therefore, they can be used as a dyes. This is the one interesting dye that is known as orange 2. It is obtained by the reaction between beta-naphthol and the diazonium ion, which is obtained from the sulfenic acid. Sulfenic acid is nothing but 4-amino sulfonic acid. Therefore, when we treat the diazonium ion, which is obtained from the 4-amino sulfonic acid with beta-naphthol, we obtain this particular orange 2 dye. And this dye was first prepared in the year 1876 and is having many industrial applications, used extensively for dyeing wool, nylon, silk and leather. Generally, the dyes will contain this particular SO3 minus Na plus moiety. Because of this ionic nature, they are soluble in the water. Thank you. Now I will discuss about the two important chemical reactions involving the phenol. First one is Kolbe-Smith reaction. The Kolbe-Smith reaction was first explained by two scientists, Kolbe and Smith. Kolbe is a very good organic chemist in the 19th century. He is the person who has coined the term synthesis. He is in fact the first person who has carried out the synthesis of acetic acid from inorganic compound carbon disulfide. He has many reactions to his credit. The famous reactions are Kolbe electrolysis and Kolbe nitrile synthesis. He has done seminal contributions for the development of organic chemistry in the 19th century. And the second scientist who is involved in the development of this particular reaction is the Smith. Rudolf Smith has modified the Kolbe reaction, and he has done the modification by taking the carbon dioxide under pressure. Let us see what is a Kolbe-Smith reaction. Whenever phenol in the presence of sodium hydroxide is treated with carbon dioxide under a pressure of 4 to 7 atmospheres at a temperature of 125 degrees centigrade, then it will change to an unstable compound, which in turn will undergo keto-enol tautomerism and will form sodium salicylate. And from this sodium salicylate, on hydrolysis in the presence of acid, we will obtain the orthohydroxybenzoic acid known as salicylic acid. We will obtain para-hydroxybenzoic acid also in the reaction, but in the minor quantity. This is the overall reaction. The phenol will undergo reaction with CO2 in the presence of base to form the salicylic acid. Here important point you have to remember is carbon dioxide acts as the electrophile. Let us see the mechanism. In the first step, phenol will undergo reaction with the hydroxide ion, and we know that phenols are acidic compounds. Therefore, the hydrogen atom present in the hydrox group is a proton. It can be easily abstracted by the base, and we will obtain a phenoxide ion. This phenoxide ion will undergo electrophilic aromatic substitution reaction with the CO2. Already we have discussed that compared to phenol, phenoxide readily undergoes electrophilic aromatic substitution reaction. It is a highly reactive aromatic system. And this phenoxide ion is resonance stabilized. These are the different resonance structures of the phenoxide ion. Therefore, phenoxide ion is a stable ion. Now, this phenoxide ion will undergo electrophilic aromatic substitution with the CO2, that is electrophile. Then we will obtain this unstable compound. This unstable compound will undergo tautomerism tautomerization and will form this particular tautomer, which is nothing but sodium salicylate. From sodium salicylate, we can obtain salicylic acid by carrying the hydrolysis in the presence of water. When we add acidic water, the proton will be added to this sodium salicylate, we will obtain the salicylic acid. Then what are the important applications of this reaction? There are several applications of Kolbe-Smith reaction. I am going to discuss about the two important compounds which can be derived from the salicylic acid. First one is aspirin, also known as acetyl salicylic acid, and the second compound is methyl salicylate, also known as oil of wintergreen. Aspirin, as we know, is one of the most widely used medicine in the world. It can be used as analgesic to relieve the pain. It can be used as anti-inflammatory drug, and also it is used as antipyretic. This is the structure of the aspirin. We can obtain aspirin from the salicylic acid by the acylation of the hydrox group. When we add acetic anhydride in the acetic acid medium to salicylic acid, then the hydroxy group will undergo acylation and it will form acetyl salicylic acid, popularly known as aspirin. And the second compound that can be derived from the salicylic acid, and which is very important, is methyl salicylate. It is also known as oil of wintergreen. this is the wintergreen tree, and the leaves of this tree are very useful because we can extract the oil from these leaves, and this oil will contain the methyl salicylate as a chief constituent. And this methyl salicylate is having several therapeutic applications. It can be used as analgesic, it can be used as antiseptic. It is having very good aroma flavor, therefore it is used as a flavoring agent. It can be used also as a perfume and also as a cosmetic compound. How we can obtain the methyl salicylate from the salicylic acid? We know that salicylic acid is nothing but orthohydroxy benzoic acid. Therefore, when we carry out the esterification of this acetic acid using methanol in the presence of an acid, then the COOH will be converted to COOCH3. That means we are carrying out the esterification of the acid with a methanol. Therefore, we will get methyl salicylate. The next reaction about which I am going to discuss is Reimer-Tiemann reaction. This reaction was discovered in the year 1866 by two scientists, Reimer and Tiemann, and the reaction was named after the two scientists. This is the overall reaction. In the Reimer-Tiemann reaction, we will convert a phenol into the orthohydroxybenzoaldehyde, also known as salicyl aldehyde. When phenol is treated with chloroform in the presence of a base, we will obtain this particular compound known as salicyl aldehyde. Let us see the mechanism. Chloroform, as we know, this is the chloroform molecule, and this chloroform molecule, the carbon atom is attached to 3 electron withdrawing chlorine atoms. They induce minus I effect. Therefore, this particular carbon atom is having a positive charge. That means this carbon atom is a acidic carbon, and the hydrogen which is directly attached to this acidic carbon is a acidic hydrogen. Therefore, by using a base, we can abstract this particular proton. When we abstract this particular proton, then we will obtain this trichlorocarbene, trichlorocarbanion, and this elimination is known as alpha elimination, because we are removing the proton or hydrogen atom which is attached to the alpha carbon atom. And once this trichlorocarbanion is formed, it will readily undergo the elimination of Cl minus chloride ion to form this carbene. This is known as dichlorocarbene, and this dichlorocarbene is a electrophile. It is a neutral electrophile. Therefore, once the dichlorocarbene, a neutral electrophile, is formed, this will readily undergo electrophilic aromatic substitution reaction with the phenol. Since we are using the acidic medium, we are using the basic medium, the phenol will be in the form of phenoxide ion, and the phenoxide ion will undergo electrophilic aromatic substitution reaction with the dichlorocarbene, and we will obtain this particular product. These are the different steps involved in the mechanism. Once dichlorocarbene attacks the phenoxide ion at the ortho position, we will obtain this particular species, this particular compound, and after retention of aromaticity, again this Cl minus will be removed. Then the OH minus ion will attack this particular carbon. Then again the electrons from the O minus will move to the aromatic system, and again another Cl minus will be removed. Like this, after several steps, we will obtain this particular orthohydroxybenzoaldehyde. In the last step, we are doing the acidic workup. That means we are purposefully adding the acid so that we can extract the orthohydroxybenzoaldehyde from the solution mixture. In the same way, we can obtain the para-hydroxybenzoaldehyde also. When the para-hydroxybenzoaldehyde will obtain when dichlorocarbene will attack the para position. This mechanism can be also represented in a simplified manner. Instead of writing all those different steps, In a simplified manner, we can assume that once the dichlorocarbon attacks the ortho position, we will obtain this particular species. In the presence of the hydroxide ion, we will obtain this dihydroxy compound, and since we know that whenever the carbon atom contains two hydroxy groups, it is highly unstable, and on heating that particular compound, it will lose water molecule and we will obtain this particular aldehyde. This on acidic workup, we can have this orthohydroxy benzoaldehyde. Therefore, instead of writing multiple steps in a simplified manner, we can write this mechanism also. Okay. Now I am going to discuss about the two important rearrangement reactions involving alcohols and phenols. The first rearrangement reaction I am going to discuss is pentocoal-pentocolone rearrangement reaction. This is the first molecular rearrangement involving the rearrangement to a electron deficient carbon, and this reaction was first reported by Rudolf Fittig in the year 1960. Let us see what is a rearrangement reaction before going to the pentocoal-pentocolone rearrangement reaction. In a rearrangement reaction, the reactants and products both will contain the same number of atoms, same number of carbon, hydrogen, oxygen and other atoms. But the only change is the carbon moiety will be different. The carbon skeleton will be different in a reactant compared to the product. Therefore, in a rearrangement reaction, an atom or a group of atoms will undergo a migration from one atom to the other atom. The atoms which are involved in the rearrangement may be the neighboring atoms or the atoms which are away from each other. Therefore, in a rearrangement reaction, an atom or a group of atoms will undergo migration from one atom to the other atom. The migrating group may be a hydride, or it may be a alkyl group, or it may be a phenyl group. If the rearrangement occurs in such a way that the group will migrate from one atom to its immediate neighbor, that is then it is known as 1,2 shift. If the 1,2 shift involves the migration of a methyl group, then it is known as 1,2 methyl shift. If it involves the hydride ion, it is known as 1,2 hydride shift. If it involves the phenyl group, it is known as 1,2 phenyl shift. And pentocoal-pentocolone rearrangement is example for a 1,2 shift reaction. As I explained before, 1,2 shift involves the migration of an organic group. It may be an aryl group, or it may be a methyl group, or it may be simple hydrogen atom in the form of H- from one atom to the atom which is next to it. If the two carbon atoms are vicinal carbon, if the two carbon atoms are adjacent to each other and they are vicinal carbon atoms, if the shift occurs between the two vicinal carbon atoms, that is known as 1,2 shift. In the pentocoal-pentocolone rearrangement, 1,2 diols are converted to the carbonyl compounds. Mostly we obtain ketones. In some cases we obtain the aldehydes also. Let us see what is a pentocoal. Pentocoal is nothing but 1,2 diol, that is a vicinal diol. That means the two hydroxy groups will be present on the two carbon atoms which are immediate neighbors to each other, and the pentocolone is a ketone. It may be an aldehyde also. Even though we are saying that it is a pentocolone, sometimes we can obtain the aldehyde also in the pentocoal-pentocolone rearrangement reaction. This is the overall reaction. This is the pentocoal which is converted to a pentocolone. That means it is undergoing the rearrangement in the presence of an acid catalyst, and to form a pennacolone. Pennacol is nothing but 2,3 dimethyl 2,3 butane diol. That means it is having two hydroxy groups and two carbon atoms which are immediate neighbors to each other. These two carbon atoms are known as vicinal carbon atoms and they are having the hydroxy group. Therefore, this is known as vicinal diol. When this is treated with the acid catalyst, then it will undergo a rearrangement to form the pennacolone. Pennacolone is nothing but tertiary butyl. This is the tertiary butyl group. This is the methyl group. Tertiary butyl methyl ketone. The name of this rearrangement is pennacol pennacolone because of this particular rearrangement reaction. That means pennacol rearranged to pennacolone in the presence of the H2SO4. That is nothing but acid catalyst. Let us look at the mechanism of the pennacol pennacolone rearrangement reaction. This reaction involves the formation of a carbocation as an intermediate. This is the pennacol. This pennacol will take one proton from the acidic medium, then we will obtain this oxonium ion. This is the oxonium ion. The oxygen is bonded to three different atoms, two hydrogen atoms and one carbon atom, and is having the positive charge, is known as oxonium ion. Once this oxonium ion is obtained, in the next step, this will be eliminated as water and we will obtain this carbocation. This is the carbocation, and we are having a tertiary carbocation because this carbon is attached to two methyl groups and also this particular alkyl moiety. Therefore, this is a tertiary carbocation. Once this tertiary carbocation is formed, it will undergo 1,2 shift. In this particular case, it will undergo 1,2 methyl shift. It is important to note that the methyl group will undergo migration from this carbon to the carbon having the positive charge along with the bonded pair of electrons. That means this methyl will move from this carbon to this carbon along with the bonded pair of electrons. Once this methyl moves with the bonded pair of electrons from this carbon to this carbon, then this particular carbon will have the positive charge. That means this carbon is having the positive charge. Then once this carbocation is formed, the oxygen will donate the pair of electrons and then we will get this particular ion. That means this particular carbocation can be resonance stabilized due to the donation of the pair of electrons from the oxygen atom. In the last step, the water molecule will abstract the proton and will obtain the pennacolone. The driving force for this particular reaction is the formation of a carbonyl compound. It may be a aldehyde or a ketone. Even though in the first step we are getting a stable carbocation, the reaction is proceeding in the forward direction due to the fact that we are obtaining the pennacolone in the final step. That is the driving force for the reaction. There are different ways of showing the 1,2 alkyl shift. The arrow notation is very important in chemistry. When we change the arrow, the chemistry will change. Therefore, we have to be careful when using the arrow notation. To represent the 1,2 alkyl shift, we are having different representations. These 5 representations can be used to represent the migration of, rather we can say to show the migration of methyl group with the bonded pair of electrons. The first representation we use this type of arrow, and the second representation we are using this type of arrow, and the third representation we are selecting the bond and also methyl group. The fourth representation we can use 2 types of arrows to show that the methyl group is actually moving with the bonded pair of electrons, and we can use also a looped curve arrow to show the migration of the methyl group with the bonded pair of electrons. And this type of representation is not supposed to be followed because this indicates only the migration of methyl group but we have to remember that in this particular rearrangement reaction, methyl group has to migrate along with the bond pair of electrons. The penacol-penaclone rearrangement reaction is a regioselective reaction. We will obtain only one product or major product that is formed from the most stable carbocation. That means whenever we carry out a penacol-penaclone rearrangement, the carbocation can be obtained from this carbon atom or from this carbon atom. The carbocation, that means we will obtain two types of carbocations. Based on the stability, one carbocation will be formed in higher amounts, higher quantities. From that carbocation we will obtain the final penaclone. And other important point we have to remember is the migrating group will never lose its configuration. The configuration of the migrating group will be retained. Let us look at this example. This is a penacol, that is a vicinal diol. From this vicinal diol, we can obtain two types of carbocations. When this particular OH group is protonated as shown here, and the water molecule is removed, then we will obtain this carbocation. And when this OH group is protonated and on removal of the water molecule, we will obtain this carbocation. Let us look at the stability of the carbocations. In this carbocation, there is a phenyl group which is attached to this positive charged carbon, whereas here only hydrogen atoms are attached. Therefore, more delocalization is possible in this case because of the phenyl group. Therefore, this is the most stable carbocation, and the final product will be formed from this carbocation only, because this will be formed in higher amounts and compared to the less stable carbocation. Now let us look at the migratory aptitude. That means we have to look at the order of migration of different groups. Which group will migrate to, from the beta carbon to the carbon atom having the positive charge. It was observed that the order of migration is hydrogen greater than aryl group greater than alkyl. You can see in this particular example, first we will obtain a carbocation at this particular OH. From this particular carbon we will obtain a carbocation. Now the methyl group or hydrogen atom along with can undergo migration to this particular carbon. Then to this carbocation, the methyl group can migrate with the bond pair of electrons, or the hydrogen can migrate with the bond pair of electrons. That means it can be a 1,2 methyl shift or 1,2 hydrate shift. But it was observed that it is only a 1,2 hydrate shift, because from this order hydrogen will undergo migration more readily when compared to alkyl group. Therefore, the hydrogen atom along with the bond pair of electrons, that is H minus, will undergo migration from this carbon to the carbocation. Therefore, it is a example for 1,2 hydrate shift reaction. The more the nucleophilicity of the group, the more readily the group will migrate. Therefore, the para-anisal group will migrate at a faster rate when compared to para-toluene, compared to phenyl and para-chlorophenyl. This particular group, anisal group, contains the alkoxy group, and alkoxy group we know is a very good plus R group, that is it will cause a very good resonance effect, and it can easily pump the electrons when compared to the methyl group or when compared to the chloro group. And this chloro group is electron withdrawing group. It will induce minus R effect. Therefore, these groups will migrate at a faster rate when compared to this particular group, that is chlorophenyl group. These are the different examples for penacol-penaclone rearrangement reaction. This is a penacol and this is a penaclone, and I have given the stable carbocations that are obtained in this particular rearrangement reactions. We will obtain the carbocation on this carbon, then the methyl will undergo a rearrangement with the bond pair of electrons. We will obtain finally this penaclone, and in this case also the carbocation will be obtained on the carbon containing the two phenyl groups, because this will be the most stable carbocation. Then the methyl group with the bond pair of electrons will migrate therefore it is a 1,2 methyl shift reaction, we will obtain this particular pennacolone. And in this case also we obtain a carbocation on this carbon, then the phenyl group will undergo the rearrangement, undergo the migration from this carbon to this carbon, and we will obtain this particular pennacolone. This is another interesting